Good afternoon, everyone. So welcome to another session of algebraic geometry seminar at the NCTS. Today we are happy to have in-person talk to have Cécile Gachet among us. So she is from Humboldt University of Berlin, and she will be visiting here until Friday. So I think her office is in the other building. So Astromas building 472. Okay, so anyway, so you you can ask me again when want to when Ceci, I will bring you to her office. Yeah, so today she will talk about I think finite quotients of linear varieties and Krepin resolution.
Yeah.
Please.
Okay, so thank you very much for the introduction. Thank you very much for the invitation too. It's my first time in Taiwan and my first time in Taipei, and I'm having a very nice time here. And it's very nice also to see a lot of you I saw last week in Tokyo, and I'm looking forward to discussing. So if you have any question about the talk or you want to talk about math, feel free to come to my office. So I'll talk about a project from a little bit ago, maybe 1.5 years ago, almost 2 years ago, from when I was a PhD student. So finite quotients of abelian varieties and Krepin resolutions. And I'll try to start with some motivation and a lot of examples. And Shui-Ying warned me that some of you are also master students, so really feel free to ask any questions. So this talk is about K-trivial varieties. So I'll just start to say by saying what K is and what K-trivial means. So definition. So we'll start with, okay, so we'll be looking at quotients that may have singularities because, you know, when you do some differential geometry, you always do smooth quotients. So you quotient by some group without fixed points to stay in the smooth category. Here we're going to be allowing to do some quotient by groups that act with some fixed points, but then maybe if we want no more singularity, we'll try to resolve them and so on. So we have to work a little bit with some singularities. So we'll start with X, a normal variety. So if you don't like the word normal, think X smooth, the locus, the sublocus where X is smooth. So X minus X smooth has dimension at most dimension of X minus 1, dimension of X, sorry, minus 2. So codimension at least 2 if you prefer. So okay, you have some singularities, but they're not too big. And then you can define some what I'll call a canonical and anti-canonical divisor as Well divisors. So they're just some sums of codimension 1 varieties. And the way we do it is first, so on U, which is just X smooth, which is a rather large open set, we have KU, which is just the holomorphic forms of the higher degree. So this is like a line bundle, and you can take some sections, and you can do minus KU as the dual. So it's you also take this as a line bundle, and then you dualize. And now the good thing is between U and X, what's left that's not U, but that's in X is of codimension rather big. So you have, if you take Well divisors on X, you have a map to Well divisors on U, and that's surjective. And here the kernel will be some cycles of dimension equal dimension of X minus 1 on, well, X minus U. But, you know, this is dimension X minus 1. And this has smaller dimension than that. So you don't have any cycles here because the dimensions don't match up. So this is just nothing. So here you have the same group. And so here we had defined, you know, this Ku and this minus Ku. But since this is an isomorphism, we get things they come from. And here we get some Kx and minus Kx here. So that's how we get those divisors. So we just throw away the singularities and we get our canonical divisor like this. And the very good news is if we do this, we'll be able to do some quotients. So for example, if we look at A, some complex torus, so we take Cn, and here we take lambda, so you should think of lambda as a lattice. So it's like Z square n times, but then you can choose a little bit how you embed it into Cn. So for instance, you can take, you know, and C, I'll do more examples in a minute. So on this one, you know, on C to the n, it's very easy to build a form in there because you take dz1, wedge dz2, wedge, etc., dzn. And so that's section of the total space on, so dimension n on Cn. So it's a holomorphic form of the volume form. But now lambda is acting by translation. And so here, if you add something to Z1, when you do D, the thing you add disappears. So this form that's defined here is actually also defined on A because it's invariant by your group action. So this is also a form on omega n of A. And so this corresponds to your Ka. And since you have this section, this means that Ka, then you could have other ones if you add a constant here. And so Ka is, as a Lombardle, is trivial. So now here it was easy to build something that to explain what Ka was, because it was just a quotient of Cn, so something very flat. And now what you could do is take a finite group acting on A. For instance, the simplest thing you can do is on C to the n, you can multiply numbers by -1. And so this is, you know, just a group of order 2, and then you quotient by this. And then on the quotient, we'll see if we still have a Ka or not. So of course, minus identity will fix some points, because if you have your lattice, so let me maybe change board and do a drawing. So just for now, we'll assume n at least 2, and I'll explain why a little bit later in the talk. And so take minus identity of Cn as a map from A to A. So maybe a good drawing is that if you have an element in Cn that's not in lambda, but 2 times this element gets in lambda. So for instance, lambda you can think is something like the integers, and you have something like 1/2. So the 2 times it arrives in lambda. Then this element is called a 2 torsion element, because when you do 2 times, you wind up in this lambda, and so you become 0. So a 2 torsion element like this would be fixed here. And so that would give you some fixed point of your group action. So you should think when you have fixed points, you get something singular. So then you can look at A quotiented by this group action. Has some singular points. In fact, it has 2 to the 2n singular points. But as you see, it is normal. It is normal since they're just singular points in dimension n. So this, I didn't define the normal, but at least this assumption is satisfied. And in fact, if you know what normal is, this is actually indeed normal. And here, if you look at this form and you try to act by minus identity, Well, each zi is going to be replaced by minus zi. So you see that if n is even, you haven't changed the form. So you still have a form, so you still have a canonical divisor here that's trivial. So if n is even, we have that this is invariant by the group action. So the canonical class of A mod, of this A mod minus I Cn of this quotient that's now singular is again trivial, just because we have this one form that trivializes it. So this is the kind of k-trivial things that we care about, and we have this volume form. And now what happens is if n is odd, when we're out of luck, because every time we act, we multiply this by -1. And so this form is not invariant, so k of the quotient is not trivial. But if we take its two torsion as a line bundle, because if we take this and we formally tensor it by itself, then we act by -1 twice. And so we're trivial again. So 2 twice this one is trivial again. And here I'm cheating a little bit, because here this thing, we were considering it as a Weil divisor. You could also think, can I consider it as a line bundle? Because maybe you're more comfortable with line bundles. This thing is actually not exactly a line bundle. This one will be. This one is just a Weil divisor, but not a Cartier divisor. But now when you go to this one is really a Cartier divisor, and it's trivial. So when you have a phenomenon like this, it will correspond to a group where you quotient by some matrices in GLN and not SLN. And you can have worse singularities, so this will be called Q-Gorenstein. If G, by which if G, so if K is not a line bundle, and this will be called Gorenstein, and so they're a little less behaved, so it corresponds to a quotient by matrices of determinants 1 kind of condition. So here you get singularities less bad. Okay, so that's just some short thing to say. We have a canonical class, a billion varieties. They always have this canonical class. That's trivial. And now if you start doing quotients, well, it depends a lot on the matrices you have in your quotient, how bad your canonical class becomes. Okay, so why do we do this? Now let's stop with this, and let's now talk about k-trivial varieties and why we should care. So some of you might know about the classification of curves of positive genus. So in genus 0, you have P1. That's a very nice curve because it's the only curve of genus 0. Then in genus 1, you have elliptic curves. So it's quite understood, like, which are the different elliptic curves, just looking at different lattices and so on. And then in genus 2 and more, well, it gets very complicated because you have hyperbolic curves and they have some moduli, and you can do Teichmüller theory, and there's much larger variety of things. Well, in higher dimension that curves, you can think of the same picture. Things aren't quite simple, but a typical way to think about it is you look at this kx and minus kx class. When this is 1 is more like positive, this is more on the side of P1, where things are pretty easy to understand. You'll have lots of rational curves, not too many automorphisms, not too many different varieties with this positive. Then when these two, well, this is 0 or this is 0, then you're in a middle ground, a little bit like elliptic curves, where it's more complicated than this, but still you can probably understand what's going on. And then when this one starts to be positive, you're more in a hyperbolic kind of place, and very bad things, complicated things can happen. And so today we work in the middle ground where this is k-trivial, so that things are simpler. So since in dimension 1, the thing you know that's k-trivial are elliptic curves, maybe we should ask what are k-trivial varieties in dimension 2. So maybe examples. Of k-trivial varieties. So in dimension 1, there's elliptic curves, and there are a few elliptic curves that we'll use later in this talk, so that I want to mention. So there are two elliptic curves that are especially nice. There's EJ and EI. So EJ, J I'll denote the third root of unity, and I the fourth root of unit that we usually use. And EJ is just what we could see by this lattice spanned by 1 and j. So you can, and EI, the lattice spanned by 1 and I. So EI maybe is the elliptic curve you've always thought about, where you take just the square and you quotient here by gluing the sides to each other. EJ, so this is EI. EJ, so is the one where you take more like a parallelogram like this, and you quotient the sides to each other. And those are very nice because they have some extra automorphisms that most elliptic curves don't have. So as we discussed before, minus identity just acts on every abelian variety just because it acts on Cn. Here you have something better because you can multiply by the third root of units because it preserves the lattice you're working on. So you act on C, and since it preserves the lattice, the action descends here on the elliptic curve. Because if you act on 1, you get this one. And if you act on j, well, j times j is j squared, which is -1 minus j. So -1 minus j is again in the lattice. And on this one is the same, right? 1 you send to I, and I times I is I squared is -1, so it's again in the lattice. So these two, they both have not just minus identity acting, but they have this little extra multiplication going on. So this is quite nice. And this one even has, you could also have some multiplication of order 6, because minus j is the 6th root of unit. So these two are quite special, and we'll have some more elliptic curves showing up later, because if you have some elliptic curves and you take their products, well, you get some abelian varieties. So now you know how to make abelian varieties, and that's all in dimension 1. So now let's do dimension 2. So in dimension 2, you have abelian surfaces, which are just abelian varieties of dimension 2. And you have something else called K3 surfaces. So for those of you who know what those are, that's very good. And for those of you who don't know, it's just good to know an example. You can think of, you take your favorite quartic equation of degree 4 and P3. You choose your equation well so that's a smooth, and then you're going to get a k-trivial surface because you have what's called the junction formula, which tells you that Ks is the same as Kp3 plus degree 4 because it's a quartic restricted to S, and now Kp3 has degree -4. -4 plus 4 is 1, so this will be trivial. So you can do a lot of smooth quartics like this. But now the good thing with abelian surfaces is their geometry doesn't depend so much of them. So for instance, they'll never have any rational curve in them. Or also the automorphism group is usually quite hard to understand from the lattice. So it can change depending on the lattice, but it's never so hard to understand. For instance, they always have some translations, and then they also have maybe some multiplications, but not too many of them. For K3 surfaces, it's way more complicated because if you choose a quartic at random, you just won't have any automorphisms. But then if you choose some special quartic, you can start having very big and very crazy groups of automorphism. So for instance, there's an example. So maybe this is a warning. Geometry depends a lot on the equation of S. And so for instance, there's a quartic. So this is an example due to Mukai and a paper in 88 that has a lot more results than this example. But let me just write this one. Look at this particular quartic plus 12x YZ4 equals 0. Well, you know, that's just one equation like this. If I tell you find the group of automorphisms of this, maybe it doesn't look so clear how you do this. Well, Mukai shows that you can find an automorphism group of order 960 that just acts here, preserving KS. So that's already very big. And this automorphism group of order 960 already has some alternating group embedded in it, which, you know, are groups that show up in classification of finite simple groups. So they're already quite complicated as far as finite groups go. So maybe that particular quartic has a subgroup of automorphisms of order 960, preserving so a certain form that's on the surface, that's a section of KS. So really like an explicit section is preserved. So, you know, this is quite big. And the thing is, maybe since you see that the geometry depends a lot on the quartic, maybe viewing it as a quartic is not a good idea. Because, you know, sometimes we want interesting examples like the special elliptic curves that are more important than other elliptic curves. And so the question could be, okay, if I care about K3 surfaces and I want to build K3 surfaces with very big automorphism group, and maybe with some fibrations to some curves, maybe with a lot of elliptic curves in them, like really interesting geometry, you know, maybe coming up with the smart quartic is not the best way to do it, because, you know, you have to pick some coefficients. It's not so easy. It feels like it's a little bit random and you don't really know where to look. And so a good idea is to say, oh, on a billion varieties, so on a billion surfaces, I understand the group, the automorphism group much better. And I understand which finite groups I can make act much better. And I understand fibrations and so on much better. So what about I start with an abelian surface and I try to make a K3 surface? And maybe that K3 surface gets a lot of interesting geometry from the abelian surface. Well, I guess the older people in the audience might laugh because this is very classical. And this is very often one of the first construction you do to build interesting K3 surface. So construction, it's called Kummer surfaces. So you start with an abelian surface. And, you know, if you just take any abelian surface, it doesn't really have any fibrational stuff. So let's just start with the craziest of all. We take E times F, and E and F are just two elliptic curves. And now, well, we just discussed if you take any elliptic curve, it's not so clear what you can make act on it, but minus identity does it. So we're going to quotient by minus identity. So here I'm going to write, for example, E times F. So I'm going to write everything with A, sorry, but in your head, do with E times F if you prefer. So here we can quotient by minus identity. So it's dimension 2. And now, so how many singular points do we get? Well, we use this formula. We get 2 to the 4, so 16 singular points. So it has 16 singular points. And so now, okay, now the question is, how do we get something smooth out of those 16 singular points? Well, I heard at lunch that some of you have done some toric geometry. So let's do it with toric geometry. So let's just zoom, for instance, at the point 0, because 0 is fixed by minus identity. So let's see what happens at 0. So we have, you know, neighborhood of 0, and this abelian surface is just going to look like C squared. So if you look at it like a fan, you just have, 1, 0, and 0, 1, and just the usual lattice of integers here. And now you quotient by minus identity of order 2. And so the finite map corresponds to, you keep the same fan, but you make a smaller lattice. So minus identity, the eigenvalues are, E minus 1 and minus 1. So it's going to be of type 1, 1 divided by 2. So it means you add here the point of coefficient 1/2 and 1/2 in your lattice. So you add a point here, and then you just have your lattice as usual, and you just add this point in your lattice and sums with it. So now you see here, if you look at this point, well, these elements in your fan, when you try to sum them, you never get to this point. So this means you have a singularity here. And to forget about the singularity, what you should do is add a ray in your fan like this. So let me draw it down here. So we're adding a ray in your fan, in the fan here. And adding this ray in your fan means you just added one divisor. So blow up the singular points. And here we added, so here we're gonna get some resolution X, but I added one exceptional divisor, and it's gonna be a rational curve. And if you look at the intersection, so you haven't done this yet, but hopefully this week, it's a rational curve. If you count it square, it's -2. And now if you try to look what happened here, you had k trivial, and if you try to see what happened here, you didn't change anything to k. So the k that we studied here. And so basically here what you can do is at those 16 singular points, you do the same thing where you can look at the fan and just add one curve blowing up at each of the 16 points. And now you get S of surface. And if you look at this fan, now it's a fan for a smooth, this is no longer singular because you get everything in your lattice. And so this surface is smooth. And then you can check that Ks is trivial. And you have 16 new rational curves that you get above all the points. 16, so exceptional curves. And the fact that you have all those 16 rational curves can prove that you actually get back to a K3 surface for those who know the definition. Because so one way to say it, for instance, you don't have an abelian surface because it has some rational curves in it, and abelian surfaces don't. And then there are some cases that would be not a K3, not an abelian, but you can also check it doesn't happen. I won't talk about it too much. So S is a K3 surface. And that's very good. And now the great thing is this K3 surface will have lots of automorphism, for instance, that come from the abelian surface. It will also have new automorphisms of its own that come, for instance, from having all of those new curves. And if you started with E times F, then here you had E times F quotiented by minus identity. And so you'd get some vibration on either factor. And here this S would get some vibrations on P1, where all the fibers are elliptic curves. And it's very nice because in elliptic curves, you have translations. You could do some translation fiber-wise and those vibrations and get a lot of, for instance, infinite order automorphisms of S. So, I was telling you K3 surfaces can have bad geometry. Well, they can even have infinite order automorphisms and infinite automorphism group. So S has a very interesting geometry. All right. But now, this is very interesting geometry, but this has been studied for a long time. So people already know many, many things about Kumo surfaces, which are those very special K3 surfaces. And so now the question is, okay, can we do something like this in higher dimension now? Well, we'll see. So maybe just to finish the list, just so you don't believe me for doing something wrong in dimension 2, this is not the only case. You could also have some free quotients of abelian surfaces and K3 surfaces, so you quotient, but by something without any fixed points. And those are, if you start with an abelian surface, those are so-called bielliptic surfaces. And if you start with a K3 surface, there's not many interesting way to do it. You just quotient by an involution that has no fixed point, and you get a so-called Enriquez surface. So this comes from K3, this comes from abelian. So, this is not all in the classification, but now with those 4 points, this is all you get as smooth surfaces with no K-trivial. So now let's move on to higher dimension. So, so now I went past the half-minute mark, so I might go a little faster. If there's anything, you can always come ask at the end or until Friday, or if it's after Friday, go ask Shui Young or Professor Junkyang or Pedro or anyone here who might know.
Also, just for some clarification, so by K-trivial, you mean numerically K-trivial. So K could
I'm a little unclear. I mean numerically because, you know, so I mean numerically because then by Boville-Bogomolov, it's also torsion.
Okay.
Yes. If you can also start off with a really, so I mean Q-Gorenstein, yeah.
Okay.
Not, yeah. Okay. So the bad news is in dimension 1, you just had the elliptic curves. In dimension 2, you have the K3 and the abelian surfaces. In dimension 3 and more, you start having 3 different pieces. So in dimension 3 and higher, we have, say, 3 types of building blocks. So maybe now let's write a precise statement. The theorem, let X be, so here I'll write a variety with, so normal, normal variety with, so for those of you who know KLT singularities, and otherwise ask for at least Q-Gorenstein here, so things are not too crazy, and just think the only singularities you want are just some quotient singularities, like you have some quotient like this, or maybe even just ask for toric singularities if you don't like quotients by non-cyclic groups or non-abelian groups. Or quotient singularities would be okay too. And Kx numerically trivial, so just when you intersect, it's trivial. Then there exists finite cover x tilde to x that is étal outside of x smooth. So if you prefer the smooth locus of x, so maybe I write like this. So the only ramification that happens is above the singular points. And x tilde, so sorry, Galois, let me explain in a second. And x tilde is an abelian variety times, it's really a product. And here those are the 3 building blocks. So this is an abelian variety. This is an irreducible holomorphic symplectic variety. And this is a Calabi-Yau variety. And if you don't like singularities, maybe put X smooth here and then you get smooth at the end everywhere and just something really étal. So this theorem is really good because it tells you those K-trivial varieties that we talk about in higher dimension, they really come from those building blocks. But let me maybe explain what the 3 building blocks are and how they're different. So the abelian varieties are those we've always talked about. That's good. Okay, so maybe let's just credit people first. So this is Bovil-Bogomolov decomposition. So you can credit it to Bovil 84 for the smooth case. And then this case with some singularities is due to a lot of people. So Greb, Genancia, Québecus, 17 plus Druel, 18 plus Höring-Pettenel, 19. And the proof uses some analytic techniques as well as algebraic ones. So for the singular case. Okay. So now the abelian variety, we already know what it is. So let's explain the building blocks. Okay, so before I explain the building blocks, saying this means the same as saying you have this x tilde and you have a finite group acting on it. And x is just a quotient by a finite group. So these are just really the quotients we had before. And now x tilde, so the abelian part we understand. The irreducible holomorphic symplectic part, so the yi, irreducible holomorphic symplectic part. They always have, so they have some symplectic form that's symplectic. So it means that you have some omega y inside, or maybe sigma y, sometimes people prefer to call it like symplectic, and y, so I just take one of them. That's a 2 form. And your k trivial from ky actually comes from sigma y. When you wedge it with itself enough times, you get the volume form we talked about first. So you might say, of course, on an abelian surface, you already have a form like this. The things that's special in the irreducible homomorphic symplectic case is that you have this form here that's symplectic. So, and sigma y wedge sigma y enough times is nowhere 0. If you do it n times. And actually, it turns out the dimension of y is an even number 2n, really. And the other special thing, so that's really special and tells you this is not an abelian variety, is, and this h0 of y omega to y, a priori, it's like a C vector space, but actually as a C vector space, it only has one generator sigma, and they're all multiples of each other. Whereas an abelian variety, you could imagine you have dz1 wedge dz2, but you also have dz1 wedge dz3, and they're not the same 2 form. So here you really have a special 2 form, and then its top power is a volume form. So for instance, the K3 surfaces are like this, because they have dimension 2. So this one is already ky if it's a surface, So these are the irreducible holomorphic symplectic part. They're a very hard class of varieties to study because the definition is not so difficult, but it's very hard to find new examples. So far, there's, if you start with some K3 surface, you can build one example from your K3 in any dimension in any even dimension. If you start with an abelian variety, you can also build one example in each dimension from it. And then you have a special example in dimension 6 and a special dimension in dimension 10. And then outside of those, like 2 big families and 2 dimension 6 and dimension 10 special ones, and then maybe some deformations of them, people don't really know any other one. And even though this definition has been existing since the 80s. So those are very hard. For those of you who look for PhD subjects, I mean, they're probably an interesting people, and let me do some advertisement that there are some people who have some money for a Hyper K grant in Paris and in Bonn, and they hire people to do this. So just to say, this is hard and very active. So, you know, this is a subject, and if you're interested, I think a lot of people here have worked on those things. All that to say, this is not what I want to talk about today. So we opened the box a little bit and took a look, but we close it again. And now we talk about the Calabi-Yau case. And the Calabi-Yau case has much more examples, but also much less theorems. So here, you know, we have fewer examples, but a lot of things that are true for K3 surfaces in dimension 2 are also true for this irreducible holomorphic symplectic ones. So for instance, you have a quadratic form, just like intersection form on surfaces that happens here. You can kind of understand where the rational curves, if you have some, come from. You can understand maybe some automorphism, birational automorphism. So this is, okay, examples are hard to find, and classification is hard, but we have some results about them. And then the Calabi-Yau, so Z, those are much harder to understand. So usually they're defined. So for today, we'll just say, for today, we just stick to smooth Calabi-Yau. The idea of Calabi-Yau is that just something that's, you know, not abelian variety and not irreducible holomorphic symplectic. And so usually the definition is going to go something like H0 of omega I of Z is, you know, the trivial vector space for all I between 0 and mz. And, you know, and for I equals mz, this is kz, so you have exactly one section, and then like, okay, and H0 of OX is like C, and H, so and KZ is really trivial, like this. Okay, and so this is not exactly the definition in the singular case, because the singular case has a more complicated definition. But in the smooth case, we'll just define Calabi-Yau this way. We say Z is Calabi-Yau if, and then that's the definition.
So you don't assume.
And I'll add it. I assume, and you can add simply connected in the smooth case. And in a singular case, you can't really add this because topology of singular Calabi-Yau can be very bad. And in the singular case, you can't just compute just some Hodge numbers on Z, but you'll have to compute them on other quasi-étale covers. So that's not very good. So that's why we only stick to smooth Calabi-Yau. And so as you see, this definition is just saying, okay, we don't have any kind of factors going on in here. This is very reducible. And we have this volume form, and we're simply connected, but that's all we know. And so if you think about, if you like equations and you start to try to generalize this thing we did with the quartic, Calabi-Yaus are usually what you get. So, you know, you start with Pn, then you take an equation, a smooth hypersurface of degree n+1, what you'll get is a Calabi-Yau. And just from Lefschetz hyperplane type results. If you do it with a Fano and you take an anti-canonical hypersurface, well, you get a Calabi-Yau again. And in a lot of cases, if there's no good reason why you should have a symplectic form on something, well, you get a Calabi-Yau. So they're more easy to build. But then again, it's not so easy, for instance, to try to build examples with very interesting geometry. So here I'll ask a question. So maybe here we start maybe the part of the talk that's not introductory anymore. So building interesting Calabi-Yau varieties. So something I have to warn you about is even in dimension 3, a lot of things are not known. But with maybe an emphasis on 3. So maybe I ask a question that I don't know the answer to, and that I'd be very happy to discuss with anyone, maybe also after the talk if they have any idea, is what is, what is the highest integer R such that you can build a Calabi-Yau threefold Z with Picard rank. So smooth Calabi-Yau threefold Z with Picard rank, rho de Z equal R. So that's a question to you. Me, I know how to do 36 and I'll explain, but I don't know if you can do better. It's no one knows a bound either. And it's pretty crazy because if you ask for Fano, well, the answer is known, you know, because, okay, in dimension 3 is classified, but in dimension 4 even, there's some recent results about how you can't get, you know, much higher than, say, 10. And if you get higher than 10, it's just you're just some product and you go maybe up to 18 or something.
So you say current record is 36.
I mean, I have never seen this question in the literature. I'm just asking here to maybe motivate. So I don't really know if people have tried to do this. I'm just saying, if I think about it like this, I thought about prepping this talk. I know how to do 36. I don't know how to do better.
Okay. So you don't know the current record?
I don't know the current record, no.
Okay.
But yeah, if you want to think about it, you know, if you can hit even 100 or something, that would be very exciting, actually. And the reason is if you start with a Fano, and if you just take an anti-canonical hypersurface, you never get bigger than the Picard of the Fano. And as I just said, for Fano, well, you don't get so high.
Yeah.
No,
So
maybe, okay,
I
so
think there's more than, so like if you take quintic, so quintic 3/4, Picard rank 1, but H12 is like 100. And you can take the mirror of it. So the Picard rank of this mirror will be 100, for instance.
Oh, okay.
Yeah, so this just another example. So
okay, so you can go up to 100, you say.
yeah.
Okay, that's good.
Probably they are higher.
Probably they are higher. Okay. But I don't know how high you can, also if there's even a bound in dimension 3.
Difficult.
It's a difficult question. Yeah, you shouldn't try to work on it too hard. It's just a good exercise to try to build some Calabi-Yau. Thanks for the example, though. Yeah. Okay, so, you know, big Picard number is a good example of crazy geometry. A big automorphism group could be another example of interesting geometry. But so I just want to do some advertisement for this method of trying to build Calabi-Yaus from abelian varieties. Okay. So maybe a simpler question, and it's simpler because it's actually already answered by someone. It's actually a very vague question. Build Calabi-Yau threefolds, resolving quotients of abelian threefolds by finite group actions. So here I'm going to make a big simplifying hypothesis. So this question you could actually also ask, you know, for any K-trivial, like try to build irreducible holomorphic symplectic things as quotients of abelian fourfold by finite group actions. This is actually possible with some big groups. For instance, you can do it in any dimension with some symmetric group acting, which is, you know, quite a big group. So there's maybe I'll write just a reference here if you're interested and you can come ask. There's a reference by Andreata and Wisniewski from 2009 that, you know, realized some things like this and then discussed some problems about building those varieties in this way. But as I told you, there are very few examples known. So if you want to take this construction to build new examples, you know, since it's been 40 years and there's been no new examples, you must really hope you have some luck if you want to just try something quite naive like this and build new examples. So, you know, it's probably quite hard since no one ever came up with it besides some basic construction here. So, you know, maybe let's not try today. And so let's think about Calabi-Yau's varieties. So simplifying, not simplifying, but so today, for the problem to be tractable, we ask the following question. So let A be an abelian variety. And let's G be a finite group acting on A. does A mod G admits a resolution of singularities X that is Calabi-Yau. That is a smooth Calabi-Yau variety. And now there's a first very naive remark, is that if there's an element in J that fixes a divisor in A, really fixes every point of a divisor, then there's no way to do this. So first remark is if there exists J and J with fixed locus of codimension 1, so, you know, not identity, of course, then it's impossible to have such an X. And the reason is actually very stupid, is that if you have something like this of codimension 1, then this quotient hap has some ramification divisor, which means that if you call it P, and here you assume you have a resolution X, then you have Kx comes from K on the base plus or minus some exceptional contribution with some coefficients. And now the one on the quotient is satisfying this thing. So now Ka is pullback of what's on the quotient. Plus some ramification divisor. So now this one is trivial. And this one, as soon as you have an assumption like this, is effective and non-zero. So this one would be anti-effective here. And if this one is anti-effective, then you can also take this and just push down. And if you push down the exceptional divisors, you get nothing. So you get that this one is anti-effective, so this one cannot be zero, because you already have this effective divisor that comes just from the image of the fixed locus. So as soon as you have some elements just fixing something of high dimension, so of local dimension, you cannot do this. So G needs to act what we'll call freely in codimension 1. So it means, okay, maybe G does not act freely, but in codimension 1, it's as if it did, because for divisors, everything is free. There's no fixed divisor. And now the question is, you know, now the point is, if G acts freely in codimension 1 and really fixes some codimension 2 something, then you can build lots of examples of this type. And you can possibly build lots of other examples, but it's actually, since you can have so many big fixed loci, it's quite hard to study. And so in this talk, we'll be asking maybe what happens if we don't only assume that, we also assume it acts freely in codimension 2. So for instance, if you wonder about threefolds, it would mean you only fix points. So this is a big simplifying assumption. It actually has some motivation in birational geometry, which I'll explain, but maybe uses a little more background. So if you don't understand it, like the motivation for it, please just take it as a simplifying hypothesis, just for the sake of, you know, at least let's study the simpler case before studying the hard case. So for today, assume G acts freely in codimension 2. So again, it only fixes stuff of codimension 3 and more. So the motivation from birational geometry is that, so if you, for instance, for Calabi-Yau threefolds, if you care about Calabi-Yau threefold, a lot of interesting geometry comes when so here we ask in the definition that the first Chern class is 0. And the second Chern class is likely not going to be 0 because you're not in a abelian variety. But you get interesting geometry when the second Chern class has some 0 intersection with some Neff divisors. And so the idea is that to have a Chern class that has intersection 0, for instance, on some Neff and big divisor on X is exactly the same as having a map like this with free in codimension 2. Action free in codimension 2 hypothesis, because action free in codimension 2 means that somehow up to H4, nothing changes between here and there. And so it means that from the C2 trivial here, you get a C2 trivial, which means if you pull back something ample here, you get something method big of zero intersection with a C2 with the right powers. So basically from looking at, Nethen big divisors on Calabi-Yau varieties that have trivial intersection with C2, which, could explain some interesting geometry, is a good reason why we'd assume this.
So are you saying that then in this case,
Yes.
C2 of x will be trivial? So C2 of x, so if such a resolution exists, is C2 of x equal to 0 in this case?
Not C2 of x equal to 0, but let me write it.
Okay.
Yes. So remark. So let x be a Calabi-Yau variety of dimension n. Let D be an F divisor on X. If D to the N is positive, so big, and D to the N minus 2 times C2 of X is 0, then there exists a birational map like this, birational proper, where A is an abelian variety and G actually in codimension 2. And it's an if and only if. And so somehow you can view this discussion as a classification of, so certain types of extremal.
Is it due to Ogiso or I forgot? At least
So I think Ogiso cites
yeah, I think
there's Shepard, Baron, and someone else.
okay.
Shepard, Baron. You can ask me later. No, I'm sorry, I forgot. It's a paper from the 90s, I think. But Ogiso uses it in dimension 3. I think they don't do higher dimension in their paper. They discuss it in dimension 3 very explicitly. But then I think the first time I read it in the higher dimension is due to Lu and Taji in a paper about like uniformization for, KLT stuff. Okay. But it really comes from the abelian variety being characterized as C2 trivial. Okay. Or quotients of abelian varieties as well. So this is, a better motivation for this also. And then the classification in dimension 3 is due to Ogiso, but that's what I want to come in a second. So, okay, so now I convinced you we need to ask for this, and I might or might not have convinced you, let's ask for this. And now we have a very nice theorem due to Ogiso from, I think, 94. That figures out and classifies completely when this happens in dimension 3, which Calabi-Yaus you can build. And there's exactly 2. So let's X be a Calabi-Yau threefold. So a smooth, Calabi-Yau threefold. Then X is a resolution of a quotient A mod G with so A abelian threefold, G finite acts freely in codimension 2, so just fixing points. If and only if A mod G is EG to the cube, so the G we started talking about it before, quotiented by JJJ, just acting as the diagonal matrix. And this one actually has a unique resolution that's Calabi-Yau. A unique Calabi-Yau resolution. Or A mod G is isomorphic to, so there's two ways to view this one. So maybe, okay. So one way to view it It's quotient by a Stickley group of order 7. And the abelian variety of quotient is 3 times an elliptic curve. And the elliptic curve is obtained in this way. You take this quadratic integer here. And now, you know, it's if you look at it in the complex plane, it's like at -1/2 here and quite high up here. So you use this 1 and 1 to make a lattice in C. You quotient, you get this elliptic curve, and then you take it 3 times. So this is a very crazy way of defining it, but you know, that's an elliptic curve. And then M7 is a matrix. So you want to make it act on the elliptic curve. So it's going to have to be in GL3 of this lattice from the elliptic curve. And how do you choose it? Well, you're very lucky and you can just choose it, find a matrix conjugate to this one. It's the 7th root of unity to the power 1, 2, and 4. And actually, you know, this is not in this lattice, but the sum of all of these are exactly this U7. So the trace is in the right ring. The determinant is 1. And you can look at, you know, the other invariant. So actually, the characteristic polynomial is in the right ring. And then you can try to reconjugate this matrix back to really get to an M7 here. So there's explicit representation as well.
So is this abelian threefold also
A Jacobian?
yeah, of a Klein quartic?
Exactly. So the other way to see it here, and that's, I think, the better way to see it for those who know what Jacobians are, is EU7 to the 3 is the Jacobian of the Klein quartic. And the Klein quartic has, you know, large automorphism group, so it has order 168. That's divisible by 7. So the Klein quartic has an automorphism of order 7 that therefore extends to the Jacobian. That's exactly what you take. Yeah. And this one, again, also has a unique Calabi-Yau resolution. Okay. So this theorem by Ogiso just tells you exactly the 2 cases that can happen. And the thing I want to tell you is just at least explain how you resolve those singularities. You know, what are the singularities in these cases? How do you resolve them? Because it's storic geometry again. And also, once you resolve, what's the Picard number of the Calabi-Yau you get, just to say, you know, where you get big Picard number, and maybe say a word about the automorphism group. So let's just resolve. So we're going to draw some fans, but you know, this is dimension 3. So instead of drawing a fan in R3, I just cut by the plane sum of coordinates equals 1, so that I can draw on the plane without doing some 3D drawings. So so how to resolve those singularities? Well, the first one. So we start in this triangle, and here, you know, this is 1/3, 1/3, 1/3 as the orders. So, you know, this is just the point in the middle here. So you're just going to blow up every time you have a singularity. So this is, you know, so sorry, maybe I should write this way. You view this one as the resolution of this one. And so this is just, so blow up. This is just the usual blow up. So each singular point 1 to resolve. And now how many singular points do you have? Well, you can count that you have 27. So 3 to the 3. Yeah. So 27 singular points. And now if you look at the Picard group that you had downstairs before the resolution, you actually have Picard number 9, because here you quotiented by something that commutes with everything. So the quotient has the same Picard group as this one first. And this one has the biggest Picard number that an abelian threefold can have, and it's 9. So so you do this at every singular point to resolve everything. And so you get this x3 of Picard number 9 coming from downstairs, plus those new 27 devices you got resolving. So that's the 36 I was talking about. And then for x7, so x7 is a very funny drawing, and it took me a little bit of time to draw it right. So x7, so that was x3. So for x7, you start with the same thing, And now the question is, how do you put your lattice points? Where it's 1/7, 2/7, 4/7. And so, of course, you can also cyclically permute 2, 4, 1 and 4, 1, 2, and you get some other lattice points. So if you draw it, it's going to look like this. And the question is, how did you resolve that? So again, you have to figure out some triangulation of this. So, you know, this is like a 1, 0, 0, 0, 1, 0, 0, 0, 1. And I don't want to make a mistake, but this is going to be, you know, 1, 2, 4/7. And then you do the permutations, but you have to put them in the right order that this is the right picture. And so to resolve, turns out you can do like this. Okay, I'll move the points a little bit so my drawing looks okay. Like this. And then you also have to get those to triangulate like that. So this is what your resolution is going to look like. And as you see, you're going to get some exceptional divisors, 3 new exceptional divisors corresponding here to those new points that you connected in this way. And turns out they're each going to be isomorphic to the Hirzebruch surface F2. And they have some cyclic intersection, as you see. So the Hirzebruch surface, so 3 exceptional divisors. And as you see, you know, this is not in the middle of anything. So you've been doing some weighted blow-ups, basically, for each singular point. So each exceptional divisor is isomorphic to the Hirzebruch surface F2. And then basically every time you can see it because this one and this one will be the same size, actually, in the drawing. And so if you look at this fan, like this is a fan of a Hirzebruch surface F2 again. And basically the fiber of one, like if you take 2 of them, they intersect where the fiber of one, a special fiber, is this negative section in the other. And it goes like this, and then all 3 of them intersect in a point because you have this common face. So it's kind of a funny picture. It's hard to imagine. But basically for each singular point, you get 3 exceptional divisors. And this, when you do this quotient, you actually have 7 singular points. You get 21 exceptional divisors. And so now if you look at, the question is also what's the Picard group you had, the contribution from the quotient downstairs. Well, here you see you've been quotienting by something like this. So maybe that's, instead of computing the Picard group, you can compute H11 downstairs. Well, you have DZ1, DZ1 bar, DZ2, DZ2 bar, DZ3, DZ3 bar. So that's 311 forms, and that's all of it. And actually the Picard number downstairs is the exact same. So you'll get 3, like rank 3. So, okay, so you start with probably rank 9. Now you go down to rank 3, and when you resolve, you add 7 for the singular points times 3, so it's 21 plus 4. So x7 with rho equals 24. So again, you know, this is quite an interesting Calabi-Yau variety. And okay, now you might tell me, I don't care about Picard numbers because, you know, that's just a number, and it being big is not good enough. And, you know, it's just a big number. It doesn't tell you anything about geometry, right? I don't care. But let me tell you more. So let's start about maybe talking about automorphism group. So, you know, every automorphism group of this one will commute with this because, you know, this is J identity. So the automorphisms of this cube of an elliptic curve, they all descend to the quotient. And actually the C2 invariant property that I talked about tells you they also all correspond to the automorphism of the Calabi-Yau you get after resolving. So X3 is automorphism group. Maybe I should erase. So automorphism group of X3 is actually the same as the automorphism group of EG3, where you actually remove the translations. Okay, maybe that's true only up to finite index. So, but we only care about big, interesting automorphisms of infinite order. So this is maybe up to finite index is true, because of course, if you have some translations by a fixed point of this one, well, it acts still on the quotients. You keep some translations of finite order, but we don't care about them so much. So this is the translation part. But still, you know, this is very big, because what do you keep? Well, you keep all the matrices and GL3 of the lattice. So this is, again, up to finite index. GL3 3 of Z brackets G. Well, that's, you know, very big group with lots of crazy automorphisms. So any matrix like this, you make it act on this cube, you descend to the quotient, and you pull it back to the blow up, and you get a crazy action. Now, what about out of X7? Well, for a while, I think everyone thought it's probably some finite group because, you know, now you take the elements here in the automorphism group, but you want them to descend to the quotient, which means you want them to conjugate M7 to a power of M7. And, you know, M7 has 3 different eigenvalues, so it's far from commuting with anything, so there shouldn't be too much stuff. But then there's a preprint by Ogiso where he actually checked that actually this group is infinite and there's some weird automorphisms in there. There's some automorphisms of positive entropy, so it was very crazy eigenvalues that act very interestingly in the Picard group. And so basically, Ogiso plus, I mean, maybe exercise, because that's not exactly what's written in the paper, but then you can check it out. Up to finite index, this will be an abelian group. And so an infinite abelian group, I'm not sure if it's Z squared or Z to the third. But the interesting thing is you get some automorphism with automorphisms of positive entropy. So actually of, you know, strictly bigger than 1 first dynamical degree. And those, they actually just come from, well, you have M7, and of course, M7 acts here and commutes with M7. And now you take identity plus M7 as something acting here. And turns out that M7 from, you know, its order and everything satisfies a bunch of polynomial equations. And it turns out that identity plus M7 acts as an automorphism here. It feels like identity plus M7 should have some kernel, but it does not here. And so it lifts. But now if you look at identity plus M7, well, the eigenvalues, they're each 1 plus this. So, you know, they're not going to have module 1 anymore. And if you look at how they act on the 3-1-1 forms, they're going to act by, you know, module squared. And so you're going to get some weird, you know, like algebraic numbers as your dynamical degrees that are, you know, some non-rational real numbers of module bigger and smaller than 1 for the different one of them. So all that to say, when you get some automorphisms of positive, so of positive entropy like this, and they have some funny action on your cone. And so somehow this sounds less interesting than this, but this makes it also quite an interesting kind of variety. And now if you care about, you know, if you care about vibration, so this one, this quotient doesn't have vibration, but now after resolution, it's not so clear if it has some vibrations or not, and I think no one really knows. And this one, well, it has lots of vibration just from the factor, just because EG squared, for instance, you know, is preserved by this. So you get some vibration on the quotient, and you get some vibrations on P1 and stuff, but they're isotrivial, so I don't know if you care about isotrivial vibrations. Okay, so that's just a lot of motivation for, you know, these are very cool examples. And then, you know, I was a young and naive PhD student, and I was, okay, let's just build more examples like this. Because, you know, these have been known for like almost 30 years, and they look very interesting, but they're too hard to work with because no one has been able to completely compute what's going on with their geometry. So what about, you know, we do something similar but in dimension 4, and we hope to have something with maybe, you know, a matrix that likes crazy, some different orders and something, and maybe we can say something about the geometry. And so, you know, I was very optimistic, and you know, you try to write some necessary and sufficient conditions. So you write some necessary conditions, and then you find some consequences. And at some point you say, okay, I have enough necessary conditions. Now I try to build an example that satisfies all these. And, you know, now I have my new Calabi-Yau and I'm happy. Well, then turns out I bought enough necessary conditions that I couldn't make a Calabi-Yau because there didn't exist any in dimension 4. So, you know, that was very sad in a way. And I don't know if there's exist any in dimension higher. So let me just write some theorems. So I'm going to write a lot of theorems, and I probably won't explain the proof of all of them, but maybe some, and we can always discuss. So some results. So this is a preprint from January 22, I think. So first theorem is so A abelian variety, J finite group. If we strengthen this assumption by one more, so act freely in codimension 3, then we lost. We can't do any Calabi-Yau resolution. Finite group acting freely in codimension 3 on A. Then A mod G actually does not even have a K-trivial resolution. Has no, and of course, if it has no K-trivial resolution, it has no Calabi-Yau resolution. Because Calabi-Yau is K-trivial plus some extra assumptions about some Hodge numbers. Okay, but it's fine because we're codimension 2, not 3. So let's keep trying, you know. Theorem 2. So let me be honest and maybe rethink in the order in which I thought about it. So theorem 2, A in abelian variety, Jx freely in codimension 2. Then A mod D has no symplectic resolution. So it has no okay, it has no of these EHS ones, but it also has none of them that has, you know, one symplectic form, but okay, not identity. Otherwise, you know, you get this, and not okay, not a subgroup, not only translations, say, you know, because of course you could just quotient by translation get an abelian variety again.
So do you use the semi-smallness of symplectic resolution to prove?
I don't know what you mean by semi-smallness, but basically I use that this is Q factorial, so there's no small resolution. Is that
yeah. So semi-smallness will imply that singular locus.
Yes.
Codimension 2. Yeah.
Yes, I use this, and then terminal is codimension 4. Exactly. Yeah. So it's very like the proof of this one. Maybe it's more proposition. I don't know. Proposition. So this one I was very happy because, you know, I want to build some Calabi-Yau ones. Well, as soon as I put this, you know, I'm not going to get anything not, I might get non-Calabi-Yau stuff. I could get products of 2 Calabi-Yau because this is not symplectic, but at least I don't get EHS, I don't get symplectic. I was very happy, you know. So now let's keep working. And then this next theorem is actually a lot of work compared to theorem 1, because theorem 1 is mostly some local arguments. Okay, if I put here 6, it's purely local arguments. If I try to refine to 3, it's still true, but it's some local and global arguments, but it's not too bad. Then theorem 2 is worse. It completely tells you what the stabilizers should be if you want a Calabi-Yau resolution. All the stabilizers, you know. So abelian variety, J finite group, acting freely in codimension 2 on A. If A mod G has a Calabi-Yau resolution, so smooth resolution that is a Calabi-Yau variety, then, so first of all, J is generated by its elements that have by elements that have fixed points. So
maybe in both theorem 1 and 2, you assume that G has doesn't act common, how to say. So if A mod G is A dot, then
yes. I mean, okay, so someone
has to have.
Yeah. Okay, so the same as here, not only translations. Yeah, thank you. If you want to not put this, you could say if A mod G has a K-trivial resolution, then A mod G is smooth and it's an abelian. Yeah, thank you. Here you don't need to put it because Calabi, you know, because if you put only translation, then here's an abelian variety, so it's not Calabi-Yau. So here you don't need to put it. Exactly. Thank you. So first of all, G is generated by elements that have fixed points. The bad news is, okay, you could have elements of G that do not have fixed points, that are products of elements that have different fixed points. And that's why, you know, this is hard, because it's really hard to understand some elements without fixed points acting on tori, and you have a lot, not just translations, but, you know, those you quotient for bielliptic surfaces. So this is kind of bad news. we have some good news. A is isogenous to ej. So okay, of dimension, we'll call the dimension n, ej to the n, or EU7 to the n. So, we get the ones from before. Cool. Now, what about the group? For every W and A, an abelian subvariety, we can look at so I wrote P stab for pointwise stabilizer of W. So it's the, it's the elements in J, such that for all W in W, G of W is W. So it's not just those that leave W invariance, really, that fix every single point. So this is going to be either Z over 3Z to some power K, or, okay, so it's a K that will depend on the W's, of course. But the stabilizers, they're always abelian, and they're always a power of this or a power of this. And actually, here I don't write, but if you get power of this, it's only in this case, and power of 7, it's only in this case. It really corresponds like this. And then 4 is actually maybe a more precise version of 3, is that in 3, you might want to represent this. So this is as an abstract group, but you also have them as matrices acting. And the point is, as matrices, they're really like, you can decompose them block by block, 3 by 3. And actually, if you decompose them block by block, you'll get that dimension of W is divisible by 3. Sorry, dimension of A minus dimension of W. So the complement is of dimension divisible by 3. And the matrices and P stabs is represented, acting on the tangent space blockwise by, you do some ones, then 3 times G, then some ones. And, the first, so P stab is going to have a first generator, whereas you have no one, just J's and then only ones. Then the second generator is going to be 3 ones, the J's and ones, then 6, the J's and ones, until you have all the J's at the bottom. So that's the P stab in this case. Or in the other case, it's going to be the same thing with multiple of 3 of 1, then M7, and then the ones. So, you can generate like this. So it's really like not just abelian, but the representation is just a sum of the representations you had before. Just you kind of move them around. And so the local picture is exactly the Ogiso local picture. You get nothing new. But now local to global is hard, again, because you could have some elements of G that don't fix any points. And, it's just the worst thing that you can imagine is if, the great thing would be if every element of G fix 0, so they're all matrices. And then you just have that G is the P stab of 0, of the point 0, and then you completely understand G, and that's the end. And you only get examples that are product of Ogiso, and so they can't be Calabi-Yau, because the product of Calabi-Yau is not Calabi-Yau. But the problem is, of course, you can have, it's like bielliptic case where you elements of G that act maybe by matrix plus translation. And if your matrix has some eigenvalue 1 and you translate along that direction, then your element doesn't have any fixed points. Or maybe it has some fixed point, but not 0. And so you can't conclude from there. But then if you're really stubborn and you want to do a lot of group theory and you have a computer with GAP installed on it, then you can actually work harder and have the computer work for you to some extent. And then you prove that if A is an abelian variety, G finite group acting freely in codimension 2. On A. Then A mod G has no Calabi-Yau, and in fact, let's write it this way, has no Calabi-Yau resolution. And in fact, if you put here no translations, not only translations, you also have no K-trivial resolution. All right. So that's that's the end of a very deceiving thing, is that we just don't get any new example besides the Ogiso one. I have like 2 minutes, right? Is that okay? Sorry? 4 or 5 minutes. Yeah, I still have to decide. Okay, so I think I know what I'll explain. So I'll try to explain how the proof is not just group theory, but is also not just algebraic geometry. So the point is that you have to make some local and global things to do this. The local thing is understanding whether or not you have a K-trivial resolution. So maybe I'll start saying the word K-trivial, I'll start saying the word Crepin resolution, because in this instance, it's exactly the same thing. And Crepin is just a more standard word. So maybe I'll start saying some buzzwords. So, this is completely local to see how we resolve your singularities. So we've done it for the toric ones. Now the problem is, of course, stabilizer here, we're very lucky they're abelian. And so, they're like toric singularities. A priori, if we just start with some assumptions like this, they have no reason to be abelian. And so we don't know how to resolve them. If we can resolve without adding any exceptional divisor in the canonical, things like this.
Sorry, so theorem 3, are there any assumptions or?
Sorry?
Are there any assumptions in theorem 3?
Like what? Dimension 4. Thank you. Yeah, dimension of A is 4. Sorry. Yeah. Conjecture is, I don't know what happens in dimension higher. Yeah. Thank you very much. So it's just the one after. Yeah, thank you. Yes. So, idea of proof, basically all the theorems happen more or less linearly. So they all have the same idea. So first of all is, one is, Cn mod G have Crepin. So Crepin is just think of same as K-trivial resolution. And the answer to this is not fully known, but everything that's known is basically has a buzzword that's Mackay correspondence. And Mackay correspondence is quite complicated, and people do a lot of research about it, even very recently. But yeah, I was very lucky that everything I care about is actually discussed in a very, not very old, but old enough paper by Ito and Rides in the 80s. I'm not sure. I think 86, but I'm not sure. So the point is that from the matrices in your group, it's quite, you cannot completely read an if and only if it has a Crepin resolution, but there are some conditions both ways. So first of all, so what they prove is like, if Cn mod G has a Crepin resolution, then G contains a junior element. And so let me just explain what junior element is. So I think this is something Reid decided to call this way, and people always ask me why. Well, the reason is he also defines a notion of age with Professor Ito, and junior is age 1. So, if you're age 1, you're junior. So that's the reason. So maybe the definition, what's a junior element? It's you take a matrix of finite order and you diagonalize it. And the eigenvalues is going to be some roots of units to some powers. So zeta, maybe that's right, zeta d to the a1 until zeta d to the an, if you're dimension n. And you can always choose your ai to be between 0 and d minus 1. And then what you call the age of m is just you sum all the ai and you divide by d. And so, if you take the Ogiso examples, it's 1/3 plus 1/3 plus 1/3 is 1, and 1/7 plus 2/7 plus 4/7 is 1. So those are junior. If you take the Ogiso example of order 7, but then you take the cube of this matrix, so you take zeta 7 to the 3, zeta 7 to the 6, and zeta 7 to the 5th, then this is not junior anymore. Because, 3 plus 5 plus 6 divided by 7 is 2. So the point is what they say is to have a Crepin resolution, you need at least one of those elements where the eigenvalues, they don't have too many big powers in them. And that's true in the examples we looked at. Well, the point is that you actually don't just need one junior element to have a crebant resolution. You can improve their result a little bit. If this has a crebant resolution, then actually your group must be generated by junior elements. Okay, so now great, you know that all your stabilizers will have some junior elements in there, probably a lot of them. But now the good news is matrices that act on abelian varieties have some constraint because they need to preserve some lattice. And, you know, for instance, if you take your matrix plus its conjugate, it's going to need to have some integral characteristic polynomial. So that gives you some constraint of eigenvalues. And by that, you can actually completely classify junior elements that act on abelian varieties with, you know, acting freely in codimension too. Not just them, but all of their powers. And you get to find at least of 12 options. So that's very good. But now it's not enough because you have 12 options and the Giza one are just 2 of them. And now the great news is that out of those 12 options, these 2 are the only one of prime order, and the other ones have some composite order. And now what you can do is quite interesting is you can count fixed points, because you know all of your stabilizer needs some junior elements. So for instance, in your list of possible juniors, you have one of order 15. So what do? You say, okay, I need this junior element of order 15. If I have one of them, you know, that's acting with some stabilizer, then I take its cube. Now it's of order 5. But I don't have any junior elements of order 5. They don't exist on abelian varieties. So now, you know, I have an element of order 5, but it has some fixed points. It has at least 1, and then I count. It turns out it has like at least 25 or so. So I get a new element that fixed in order 5, but not by my first junior. For this new singularity that I get to, you know, also have a crebant resolution, there needs to be a junior there that, you know, makes this singularity better, and is a junior element that makes everything good again. So I get this new junior element that fixes a new point that's of order 15 again. And so now I start building, you know, I have a lot of fixed points like this. So they account for too many junior elements, but each time I have a new junior element, you know, if I take to the power 3 and I get some new thing of order 5 and I get some new fixed points. And at some points, the order 5 gets so many fixed points, I can't have enough junior elements to, you know, account for it. So that's the idea of the proof. And every time you have something composite of a composite order, you can do something like that. Except order 6 is harder because, you know, 2 times 3 and 2 and 3 are small prime numbers with lots of problems. So those are harder, but you remove all of them except order 3 and 6. And that's how you go. And at some point, you need the computer and some Taylor theory and some group theory, but you know, it's not just group theory. You really need to count some fixed points into some global arguments too. So that's it. Thank you.
Thank you very much for the very nice talk. Are there any questions?
So you fix a quotient like A quotient by G, and suppose it has a Calabi-Yau resolution. Is this resolution always unique?
No, 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 no. So in this case, it's easier to see if it's unique or not, because in toric geometry, so, you know, if it's not, what you could imagine is you have some flops of the Calabi-Yau. But if you look at something where you have a toric resolution, a flop corresponds to you have a quadrilateron with a diagonal, and a flop is you remove the diagonal and you put the other instead. But the thing is, if you look at this one, if you remove a diagonal like this is a line, so you can't flop. So there's no way to flop from this one. So in this case, it's unique. And from this one, it's quite clear you can't flop either. But yeah, there could be several of them. For instance, for X7, okay, so for instance, for X7, it's not clear if there's other ones or not. So it's unique crebant resolution with a map to this one, but then you could flop it. Okay, for instance, X7, and we don't know if it has flops or not. The only thing we know when I say unique here is that there's no, if you flop, then the map that we used to have from X7 to A mod G will no longer be well defined. And you could imagine other example that those 2 where it's unique, where you have some quotient, you have different resolutions. Yeah.
So in the third point of theorem 2, does in particular imply that every abelian subvariety has a stabilizer? So yeah, so P stable is 0.1 stabilizer is always non-trivial.
No. It's you can put 0 here and here. Yeah.
Ah,
You can have most of them will have trivial.
then the 0.4 is
Okay. Okay. Not the. I mean, if
assume that it's
okay. 0.4 is if non-trivial.
okay. Okay, I see.
So if yeah. Thank you.
And if this is non-trivial, then does it mean that W is is always of the form ej to the k times 0 up to permutation of factors?
Yes. Up to isogeny, not up to isomorphism, unfortunately.
Yes.
Because this if you have this action, you're really isomorphic to eg to the cube.
Mhm.
But then if you have it on a summon and on a thus summon, you could have some isogenies because you don't have any automorphism that force it to interact. Yeah.
And do you have the control of the degree of isogenies?
No, but I also don't know very much about isogenies, so maybe someone could get it. I couldn't. Yeah.
Mhm. So are there other questions?
So here you always assume the Athene 3D in codimension 2.
Mhm.
So what happened in the case where Athene is in codimension 1? 3 in codimension.
Lots of things. So there are lots of examples, first of all. So every Kummer type hypercolor can be realized allowing this. And we started a project with Christian Lehn and Salvatore Flocari about trying to understand some things like this. But I think it's very hard and there are many examples. It's also hard to build new examples. So
even in dimension 3.
in dimension 3, I don't know. I didn't try, but yeah.
Maybe Kummer K3 times elliptic curve is an example, but are there other?
Okay, no, but non-product, yeah. No.
So like really Calabi-Yau.
Yeah, I don't know. So the thing that's changed in the proof, if you do what you suggested, so you allow codimension 2, is you just get more juniors. It's still finitely many options, but instead of like 12, you get maybe 15 or 20. And the other problems is you get a lot of juniors of form like -1 II, and then you can add 1 as always. And so the thing is, in the 12 juniors I get, all of them except 1, all the eigenvalues have the same order, and so it's not 2. And so it's very good because it tells me that I have some complex multiplication, a billion subvariety. But if you have something like this, you know, this is order 2, so it doesn't tell you anything about the underlying variety. And but it should be in dimension 3. It should be possible. I don't know. Thanks for the question.
Is there a toric argument for Ogizos' theorem? So the existence of only 2.
No. I mean, I think so. He proves all the necessary conditions to go down to these, and then he says there's resolution at Calabi-Yau, and that's a toric argument. But no, because the hard thing is prove it's abelian. Once abelian, it's not so hard, I think.
Okay, so toric only gives you local.
Yeah. Yeah, the Giza paper is also very nice to read because it's quite short. I think I remember it to be 7 pages or so. And the argument is very, very beautiful.
Are there more questions?
I wanted to ask about, so in theorem 3, you do allow that it's smooth, and then you're saying the structure, the canonical is trivial, or am I misunderstanding?
So which smooth? This one?
Yeah, the quotient.
So basically I say, okay, so there are 2 theories. I mean, okay, so there's one way to read this just to say it has no Calabi-Yau. So if you allow to it be only translations, then there's no Calabi-Yau one.
But even if there's if there's things which are not translations and the quotient is smooth, you're saying that the canonical cannot be.
Sorry, no, you're right. Not really. Yeah, because you have all the de Meitner examples, you know, about not free action. Okay, if you ask for a non-K-trivial, yeah. Because the canonical, yeah, I mean, sorry, it's a very good one. If you have a free action, the canonical is going to be trivial, yeah. Yeah.
Okay, so are there more questions? If not, then let's thank Ceci again. Thank you very much.